Welcome to a special field edition of Truckee Talks. On July 27, 1997, President Clinton and Vice President Gore spent some time on the Tahoe Research Group's research vessel, the John LeConte. Here they are meeting Dr. Charles Goldman and Bob Richards. Dr. Goldman heads the UC Davis Tahoe Research Group, and Bob Richards is director of the Field Research Laboratory in Tahoe City. Together they have been collecting data from Lake Tahoe since 1958 and 1969 respectively. Dr. Goldman made an alarming statement during the presidential summit on Lake Tahoe. Here it is.
What we're seeing is the greening of Lake Tahoe. We saw the Great Lakes go into a catastrophic condition over a period of only a few decades from urban development, from pollution, from fertilizers, and particularly from urban sewage. And at Tahoe, we have one of the clearest large lakes in the world, and we're losing that transparency, and Tahoe is revered for this cobalt blue water. If we don't turn this around, this progressive greening of Lake Tahoe, within the next 10 years, it'll probably be too late because the lake has such a long retention time. The water stays in Tahoe for an average of 700 years.
Then President Clinton gave the UC Davis Tahoe Research Group a large responsibility.
Second, we'll take steps to protect and restore the lake's fabled water quality. We will work with UC Davis to develop computer tools that can predict how various watershed improvements will contribute to water quality. Every federal agency here will work to increase efforts to restore natural habitat, reduce erosion, and keep the water clean.
I thought it best to check out the science that led to Dr. Goldman's conclusion and the new responsibilities bestowed by President Clinton. Was this just more of the knee-jerk ecological hysteria so common today, or was it based on good science? Captain Bob Richards was nice enough to let me tag along during the day of testing. My Schneider was busy working that day, so you're stuck with me, Gary McNally, asking the questions. Here's Captain Bob Richards.
We're ready to lower the Van Dorn water sampler down to collect water at different depths, down to over 105 meters, which is about 350 feet. We'll start off with the subsurface sample, and I lower this down and then release this messenger weight down, which hits the top here, flips this lever over, and both ends close, and then we can bring it back up to the surface and draw off our water samples. So we'll take her down to the surface now. Lower the weight away and check and make sure our meter wheel is on 0 so we can get the right depths as we come back up. Then we just start filling bottles. We have 3 bottles for the algae growth rate samples. One of them is enclosed in tape to measure respiration rate. And the other 2 are clear bottles so that the algae can photosynthesize. And this big bottle is for various forms of water chemistry and chlorophyll and things like that. We measure the nitrogen and phosphorus compounds content at every depth, and we will also take some algae samples at some depths. Then we go back down and get another sample, 2 meters next. We take more samples near the surface than we do down deeper because that's where more of the action is as far as the algae goes. There's more sunlight up here, of course, and they use that for photosynthesis. Okay, 2 meters. Okay, we'll refill another set of bottles, same way. There is a difference with the depth, of course, because of the light penetration, and it also differs seasonally because of the nutrient content of the water that allows the algae to grow, and the amount of sunlight that comes in varies, of course, over the year from summer to winter. Temperature also varies. So we do see a lot of changes. There's actually a little less growth deeper because there's so much sunlight that the algae don't grow too well. It's called photoinhibition. But if you get down 15 or 20 or 30 feet, then you find a greater growth, because that's where the optimum conditions of light and nutrient content are. At this particular depth, we'll take one extra sample for the amount of phytoplankton or floating algae that's in the lake. It'll be the next bottle, and you'll see it has an iodine colored stain in it, which is used to preserve the algae, and also it stains them so that they're more easily identifiable under the microscope. We've been doing these samples at this particular station year-round since 1967, so we really do have a good long-term data set, which is really what you need for environmental ecological studies, where you're trying to determine long-term changes in lakes. There's not very many data sets around the country that have this length of sampling. Unfortunately, most places, they only have money to do research for maybe 2 to 5 years, and then they have to move on to something else because the funding runs out. And Dr. Goldman, who's the head of our project, has been able to keep the money coming in pretty steadily over the years, and that's allowed us to gain this valuable insight on what the long-term changes are at Tahoe. So from now on the way down here, it's pretty much repetitive. We just keep doing the same things over and over again.
You've been doing this every 10 days since 1967?
Yeah, I've been up here since '69, but the project's been year-round since '67. And Dr. Goldman first came up here as early as 1959 and 1960 and started sampling out of a small rowboat over off of Cave Rock. So that's when our first samples were collected. And we've seen a huge increase in the algae growth rate since that time. It's gone up by about 5 to 7% per year on the average over the long term, and more than quadrupled in that period of time, which is a significant rate for a lake that should slowly age, but not age and change and increase its algal growth rate this quickly. And most of that is due to the influence that man is having upon the environment, both within the basin and from outside the basin.
Like the pollution in the air dropping into the lake from the rain?
Yes, yeah, we're getting large amounts of air pollution that are coming in. Determined that well over 60% or 2/3 of the nitrogen input to the lake, which is one of the major algae growth components, comes from the atmosphere. It's both locally generated from automobiles and other forms of air pollution, and also it comes in from over the hill from Central Valley and from the urban areas to the west of us, Sacramento, probably from San Francisco area too. So there's a lot of different forms of additives being put into the lake, a lot of different nutrient sources which fertilize the algae growth. One of the things that we're trying to control is the amount of phosphorus that comes in, and that's linked to erosion. So if we can control the erosion rates, we can probably control some of the algae growth rate. And that's why the Tahoe Regional Planning Agency has such a great emphasis on erosion control projects, because that's one thing that may be controllable to stop this continued decline in water quality.
Is Lake Tahoe somewhat unique in that the drainage from the lake takes so long?
Yes, it is. The lake has what we call a very long residence time for the water that comes into it. If you were able to take the lake and tip it up on its side and dump out all the water and then replace it at the normal rate of snow and rain that comes into the lake, it would take between 600 and 700 years to replace that water back up to the rim. And that's the problem with Tahoe. It doesn't have a very short residence time or flushing time, so that essentially everything that comes to the lake is going to stay in the lake for generations. And that's the great danger with Tahoe, is that what we put in here now is going to stay here for decades, if not centuries. Many lakes have the ability to flush themselves quickly and to repair themselves because of that. But Tahoe doesn't have that luxury because of that long residence time. So all of these nutrients that are falling out of the sky and entering from the streams and so on are essentially going to stay here for a long period of time. So if we don't turn it around pretty quickly, we're going to have a very difficult time turning it around at all. There's a huge volume of water out here. It's enough to cover the entire state of California 14 inches deep.
Now, the plankton eat the algae, but there's no way to import plankton, I guess.
Well, no, their levels sort of depend on what kind of algae food sources are available. So you really can't import them to the lake over and above what the lake will support. There have been a lot of introductions of exotic species into the lake. In fact, all those sports fishes in Tahoe are not natives. And there's been the introduction of a shrimp into the lake too, which was to supposedly help support the fishery. And it caused some major environmental changes in the lake and actually wiped out a couple of the major zooplankton species, animal plankton species in the lake. So it's putting exotic species into an environment where they're not normally found has a lot of potential hazards.
When were those shrimp introduced?
They were introduced in 1965 by California Nevada Departments of Fish and Game with the express purpose of supporting the mid-sized trout in their to help supplement the food supply for the mid-sized trout. And they were brought down from Canada and imported into a lot of different lakes all over California. And they had some success in a few lakes, and in Tahoe it was not too much of a success because of the shape and size of the lake. It didn't work out very well.
So they died out?
No, they're still here, and they'll be here forever unless there's some natural catastrophe that removes them.
And so they're eating up the plankton?
Yeah, they turned, what they did was they pretty much eliminated two of the major species of animal plankton that were in the lake that supported the juvenile fishes in the lake. Things we call cladocerans, and they were both pretty much wiped out by the predation of the mysis shrimp, the opossum shrimp. Well, we're down to 40 meters now, and I can distinctly feel a difference in temperature in the water. It's getting quite a bit colder.
During the drought years, does that cut down on the sedimentation and the algae growth?
It appears to have cut down a little bit, yes, because during drought years you're not getting as much precipitation, of course. Therefore you don't get as much nutrient input directly from the atmosphere, and it also cuts down the erosion because your streams aren't flowing as high. So there does tend to be a temporary clearing up of the lake water and a reduction in the algae growth. Although it's also linked to how deep the lake mixes, because Tahoe has a property in late winter, say the end of February and early March, to mix all the water from the top to the bottom if you get enough cold weather and windiness during the early part of the winter, so that the nutrients that are stored down at the bottom of the lake can actually be brought right back up to the surface, and it allows for increased algae growth. So this sort of sometimes confounds the picture when you're looking at just the nutrient inputs from the surface. You also get nutrient inputs from the bottom of the lake, and that causes some problems in interpretation of the data.
So conversely, after these last two wet winters, has the algae growth increased?
We don't have the data yet for this year because we're always about a year behind in interpretation of it. It looks like actually last year, because we didn't have a really complete mixing, there was not as much growth as we expected. And the lake, in some ways, actually cleared up a little bit. But it'll be interesting to see what the floods from this last winter during the New Year's period, what effects those have upon this year's algae growth. The water transparency hasn't been remarkably good or bad the entire year. We've been measuring it with a Secchi disc at around 20 meters most of the year.
Speaking of sewer, how long has it been since the sewer's all been transported out of the basin?
At Lake Tahoe, the sewage has been exported pretty much since the middle of the 1970s. And that's probably helped a lot. It's really hard to tell, of course, because we haven't had the sewage inputs. Early on up here, one of the things that people wanted to do was to build a pipeline from the sewage treatment plant into the bottom of Lake Tahoe and dump the sewage there. And if they'd done that, we would have had a very green lake by now, because even though the sewage was treated and not a health hazard problem, it would have definitely contributed a lot of nutrients to the water column, and the lake would have been in much worse shape than it is now. So sewage export has been a very positive thing for Lake Tahoe.
Is it your group that came up with the near $1 billion figure to restore the lake?
No, that list of expenditures was actually compiled by the Tahoe Regional Planning Agency, and it's based on what they perceive as the necessary needs in building erosion control structures and revegetation and sort of remediation of past problems at Tahoe to correct the problem. And so that shopping list of projects that needs to be done was determined by them. What we've basically done is provide information to show them that some of these projects really are necessary in order to curb the continued decline of the lake water quality. If we can't control the nutrients that are entering the lake, there's not a whole lot of hope for turning the lake around. The presidential visit has brought in a little bit of new money too, which is going to be helpful in doing things like repairing the sewer line at South Lake Tahoe, so they don't have to be continually hounded by breakdowns. It should also improve things regarding some traffic problems that we've had by beginning home or area mail delivery in some places like along the west shore of Lake Tahoe. Also, I guess they're going to change the mail vehicles into propane power in order to reduce the emissions into the atmosphere. So all those little things are going to help somewhat. Got about 3 samples to go, and then we'll take the bottles inside and inject them with a carbon-14, which measures the algae growth. And then we'll put the bottles back down in the lake on a float for about a 4-hour period, some of them anyhow, to measure how fast the algae grow at different depths.
Those stumps they found below the surface of Lake Tahoe, there was no way to measure the algae from 5,000 years ago, was there?
From sediments?
Yeah.
No, although you can determine past history and sedimentation rates by looking at the sediment cores and get some idea of what the historic rates were versus what they are now. We actually have a graduate student who's doing that kind of work right at the moment. We have some large sediment traps out in the lake, and he's collecting the sediment every 90 days at several locations, trying to determine the sediment rates that are going on now. And then he also collects bottom cores out in the middle of the lake and checks them by dating methods to find out the rates of sedimentation in the past.
But right now we have no data for the past?
Yes, we do. Yes, there is some from a couple of hundred years worth anyhow. And it shows that there were periods of higher sedimentation and lower. It was higher during the period of logging back in the 1800s when they were supplying mining timbers for the Comstock lode in Nevada. Apparently there was a fair amount of erosion then, and then there was some repair of the watershed because the sedimentation rate slowed down, and now it's increasing again.
That first point then during the Comstock period?
Yes,
So any way to figure on the Secchi disc measurement what
no.
was?
Well, we have a few measurements that were done by John LeConte, who this boat is named for, back in the 1800s. He made some measurements and during the summer, but only a few, so it's fairly hard to compare his with ours. Generally his were as good, if not better, than ours, which you would expect because the lake water quality was better then, but he didn't do them on a year-round basis the way we do here. We collect about 30 to 35 different measurements per year at this one location and then look at that over the long term. And that's where we've been able to determine that the lake is losing its clarity at well over a foot a year, which is very, very rapid.
You get to go out on the lake with President and Vice President?
Was I out getting water with them?
Yeah.
Yes,
How was that?
That was okay. It was fun to have them out on the boat and to get them to really be able to see how we collect the information about Tahoe. And it was a good time with both of them. They were quite knowledgeable, and Vice President Gore was filling in the president as we were sitting out there on some of the problems associated with Tahoe, and I think they both got a pretty good crash course in limnology or inland studies of lakes very quickly. This is the last sample, 105 meters. It's the one I've been looking for all morning, the last one. And we'll take these algae growth rate bottles, the 3 first bottles that I fill, into the cabin with the others, and then inject them with a carbon compound called carbon-14, and that is the thing that measures the algae growth rate. We'll put them back out on the lake to incubate at the same depth, temperature, and light that they were collected at, and then after 4 hours pick them up, filter them out onto fine porosity filters, so the algae are trapped on the filters and the water passes through. That way we can measure the growth. It's good, clean, clear water from the bottom of the lake here.
No Giardia or whatever that is?
No Giardia. Well, there may be a little bit, but it's so diluted by the volume of the lake that there's not much chance of getting it here. Sodium bicarbonate with a carbon-12 atom has been tagged to make it carbon-14, which is a slightly radioactive carbon, and that's how we can tell if the algae growth has occurred, because the algae take up this radioactive carbon just the way they do the regular carbon. and they become slightly radioactive, and then we can count the amount of radioactivity that's in each algae sample after the 4-hour incubation and find out how much growth occurred. So from every depth I'm going to inject a half a milliliter of the carbon-14 into each bottle, and then close up the caps and mix them, put them back down into the lake at the same depth that they were collected, and leave them on an incubation line for a 4-hour period. Excuse me, what we're going to do now is lower this anchor line away and clip the bottles that we just took out of the lake back on to this particular line in reverse order, starting out with a 105-meter sample and working back up to the surface. And we'll anchor the line here and leave it for the incubation period. Around each one of the light bottles we have little light protection socks in order to keep the algae from getting too much sunlight up near the surface here when we're handling them, because the algae can undergo something called photoinhibition, which actually inhibits their photosynthesis, and so we try and protect them from the light and not keep them out in it too long. Okay, we're going to attach this float to the line and then set it adrift here. So bottles went in at 10:12, and we'll pull them out at about 2:12. Give them a 4-hour incubation. Okay, what we're going to do now that we've got the bottles in incubating is put a plankton net over the side to measure the population level of the animal plankton, which we call zooplankton. These are the little microcrustaceans that live in the lake, and they're the ones that graze on the algae. We're going to see how many of these we can collect in a net tow. We put this little bucket on the end here and to catch all of the animals. This net acts as essentially a gigantic strainer to collect the plankton out of the lake. We lower down to this level here and then check the flow meter to make sure the numbers are recording. This tells us how much volume of water comes through the net, so we can make an estimate of number of animals per liter of water. 3886. Okay, send it on down. What I do is lower this down to 150 meters and then tow it directly up vertically to collect the entire water column. Lower away this temperature sensor here. It's called a temperature data logger, and what it is a thermistor or temperature sensor that once it's armed will record temperature to the nearest 1/10 of a degree centigrade from the surface down to about 120 meters. I have to turn it on with a little switch here called an LED switch. Take out this one little shorting plug and then add in this one here, and that basically turns it on for us. Yep, the little light's on, so now we can lower it away. Then we take this back to the laboratory and dump the information into a computer, and it gives us a temperature profile.
Have you always been doing your samples at Homewood?
This has been our index station all these years, except for the initial samples that Dr. Goldman took over near Cave Rock back in '59. But since 1967 to the present, this has been the location. We've also sampled all around the lake on occasion and collected like 30 different stations just to measure the aerial variability in algae growth. And we settled on this one for two reasons. One was convenience and logistics, and also it turns out the station. It's not the highest growth rate and it's not the lowest. See what our meter wheel read. 42.95. Okay. And see if we got anything in the end. And I'm sure we did. You wouldn't think that there's a lot of plankton in this lake, but when you concentrate a water column that's 150 meters in length and about 3 feet across, you get a lot of them. The plankton community in Tahoe is, because of that introduction of the shrimp, has been simplified somewhat. And there's really two major species in the lake now that you can see easily. There's some smaller forms called rotifers, which are also present, but they're pretty small and they're hard to see. But these two forms are called calanoid copepods. They're microcrustaceans, and they're quite prevalent. You can see them. If you look down in here, you can see quite a concentration of them. We'll get rid of a little bit of the water here. And then put them in a viewing chamber. Take a look at some of them. And then we'll preserve the sample for later. There's two species in there mainly. One is a very red one, which you can see quite easily. And the other one is sort of a flesh color. The red one is called Diaptomus. And the reason it has a red color is that it has the ability to concentrate a pigment called a carotenoid. It's the same pigment that you get in carrots. And they, in turn, impart this pigment color to the fish which eat these animal plankton. Stick them in this little viewer here, we can kind of get an idea of what's in there.
Now these are in real small amounts. They wouldn't affect the clarity of the lake, would they?
They can if they get concentrated in large amounts, but you're right, they don't normally give the lake a huge color and loss of clarity. We're getting a lot of juvenile ones right now. Tremendous numbers of young. It usually happens at this time of the year. And I would say the red ones outnumber the whitish ones, which is called epicura, probably 20 to 1 present time. It's a real mishmash of organisms in there now. And there's a few large algae that you can see as well in this. Most of them are pretty small, and they tend to be smaller than you can see in this particular viewfinder. So we'll take this sample and actually add some soda water to it in order to anesthetize the animal plankton, so that when you count them, they're much easier to count. So we'll concentrate these down and put them in a jar.
They don't move around, in other words?
Yeah, that's what's going to happen to them is that after we anesthetize them, then they're preserved in formalin to be counted at a later date.
I see.
I'll add some CO2 here. Give them a little party here before they depart. PAR meter, which measures photosynthetically active radiation. And we're going to lower this down over the side and take measurements at the same depths that we have the algae samples incubating in the lake to measure what the light climate would be at those particular depths. And we'll gauge this underwater photocell against a deck photocell, which is up here on the boat. So we'll take readings right at the surface and then about 13 to 15 measurements on down through the water column. I have to zero the meter wheel here to make sure we're at the right depths. And then record down here on this deck cell readout. All right, what we're going to do now is take a transparency measurement using the good old-fashioned method of a Secchi disc, and we lower this down in the lake until it just disappears from our view. We measure the depth on the meter wheel up here and then raise it up until we can just see it again and take that reading and then average the two. So if on the way down the depth is 21 meters and on the way up it's 19, that for the day the Secchi reading is 20 meters. This is a method that's been used worldwide to compare oceans and lakes for many, many years. It was invented over in the Adriatic Sea by Antonio Secchi many, many years ago when he worked in the Pope's Navy. So we'll lower it over the side here now. And we have to remove our sunglasses so that we don't change the results a little bit. And we always take it right around noontime on the shady side of the boat. And the readings today should be pretty good because it's very, very calm. All right, we're down to about 20 feet already. The disc is brightened up now because it's come underneath the boat, so sunlight's reflecting off of it. We're down over 30 feet now, or 10 meters. And we'll lower it down until we reach the point of extinction where we can no longer see it with a naked eye. 15 meters. Still going. You can see there's some sky reflection on a calm day like this. You can still barely see it. Just a little bit farther now. Okay, we have about 23 meters down. We'll bring it back up until we can just see it again. Up to 22 meters. So if we average those two values, the reading then is 22.5 meters for the day. It's beginning to clear a little bit compared to what it was in midsummer. It was down around 18 or 19 meters. And the clearest time of the year is usually during that period of mixing or overturn in late February or early March. And then we can occasionally get Secchi disc readings well over 30 meters. We're also going to do a black Secchi disc here for another type of measurement. It's a little larger. This is sort of a different type of measurement that we're just experimenting with now, just to see if we can see a difference in the clarity using this method, which is used by some people in oceans. Are there many lakes that are monitored this way? Yes, quite a number. Many of them don't have the amount of monitoring that goes on here at Tahoe, but there are many lakes in the world that are monitored on a routine basis, and they do check the clarity like this.
Lake Tahoe the clearest?
No. Crater Lake in Oregon is one of the clearest large lakes now. Crater Lake and Lake Tahoe 30 years ago were the same clarity, but because of the influence of urbanization in the Tahoe area, we've lost it, so that they rarely compare with each other anymore now. Crater Lake, of course, is protected by being in a national park and not having too much urban influence from the airshed to the west.
Is there any hope of Lake Tahoe becoming a national park?
Not any longer, I don't think so. I don't think there's enough money around to buy it all out. There was a chance and an opportunity back in the early part of the century to turn Lake Tahoe into a national park, but they felt that the price was too high at that time, and that the land had been degraded because of the Comstock logging. So the Congress decided that that was not a good thing to do. And now there's so much development that I doubt it would ever become a national park.
What kind of clarity is Crater Lake
It's routinely getting around 30 meters. And on occasion they'll get up to 40 meters. So it's quite a bit deeper. Okay, the black Secchi was, like I said, just about half of what the white one was, by contrast. It's just taking a little bit of water from each depth and making what's called a composite sample. And we essentially, theoretically, divide the lake up into different layers, sort of like a layer cake, and withdraw a volume of water corresponding to the size of that layer in the lake to make up this composite sample, and that an average value for the amount of algae that's in the whole water column that way. Ideally, you'd like to be able to take a sample for every depth and count all of the algae in it, but it's a very expensive proposition to do that, so we try and economize and compromise and take fewer samples and still give us some idea of how many algae are in the lake at different levels and in total. Because to count every single sample costs anywhere from $50 to $100 per sample, and we've collected thousands and thousands of samples, so it becomes a very expensive proposition. So here's another one of our algae samples. It's a composite for the shallow water for the Secchi disc reading. And then we're going to do another one that covers the entire water column of samples we collected. And again, we'll just take a little bit of water from each bottle. We save the rest of this water for analysis back in the laboratory for something called alkalinity. And also occasionally we'll do a chlorophyll sample. We just need to limit our use of the things like the internal combustion engine in the Tahoe Basin if we want to keep it from being degraded. It's going to be a very difficult battle because, as you well know, Californians and others are in love with their automobiles.
Golf course fertilizers have something to do with it too, huh?
Yeah, fertilizers of all forms. Those used on golf courses, those used in lawns, those for flower gardens. All of those things have nitrogen and phosphorus in it as part of the fertilizer compounds, and they grow algae in the lake just as well as they grow grass on land. People are trying to utilize fertilizers that are a little better than they used to be, you know, time-release fertilizers and those sorts of things. But it still takes some fertilizers to allow exotic plants to grow in the basin and keep them fertilized and growing. So they all contribute to the water pollution if they're not totally utilized by the terrestrial plants. So if it gets into the groundwater, it eventually makes its way to the lake through seepage underground or re-entry back into stream courses and then into the lake. So fertilization is a big problem up here as far as algae growth goes. So here's a composite from the surface down to 105 meters. And then we'll take a 100 milliliter sample to measure the chlorophyll content of this composite. Gives us an idea of the sort of the biomass of the algae that's out there in the lake. And we'll filter that through a little fine porosity filter over here with a hand vacuum pump, since it's only one sample. And then freeze the sample for later analysis. So we're just sucking the water through onto a glass fiber filter, concentrating the algae and allowing the lake water to go through. And then we'll put some tape on the little dish and put it in the freezer compartment. Are you ready? Okay. Okay, we finished filtering the chlorophyll sample out now, and we'll remove the filter from this manifold here, put it in a dish, little aluminum dish, and then cover it up to exclude the light, and then tape the dish shut, put it in the freezer for later analysis. And it'll give us some idea of what the value is for the chlorophyll content of the lake in a composite sample. Put it in the freezer over here. And that's it. We're done with the morning sampling. We'll go in and take a little bit of a break, eat lunch, and get ready to come back out and pick up the other bottles. Well, we're retrieving the bottles now after their 4-hour incubation. We'll bring them back up and put them in a light, tight box to protect them from any more growth. Keep them out of the sunlight as much as possible before we filter them. out on defined porosity filters. This is to collect all the algae on the filter and allow the water to pass through. So for each depth we had 2 clear bottles and 1 covered one, and we'll do the clear bottles first to stop the photosynthesis, and then we'll do all the dark bottles, the black bottles, afterwards. Sometimes these tops stick on me. There we go. Yes, yeah, these are the ones that have been incubating for 4 hours at each one of the depths that they were collected. So the algae have taken up the normal carbon in the water, carbon 12, and they've taken up the carbon 14 as well. So they're slightly radioactive now. And so all the algae are filtered out on the filters, and then we take them and put them into a Geiger counter, and it counts the amount of radioactivity on the filter, and that's proportional to their growth rate. Done there is put little rings on each one of the filters so that they dry flat in order to allow them to go into the Geiger counter correctly. If they curl up, sometimes they get stuck in the mechanism.
Well, that's the highlights of the field research. I'm not a scientist, but it looked pretty thorough to me. If anyone is interested in a future story on the lab work or has some doubts about the science already shown, give me a call at 587-8306. On behalf of Maya Snyder, John Eccles, and the rest of the Truckee Talks team, I'm Gary McNally. Thanks for watching.